Okay, so today you just learned about fission and fusion. You've already seen Chernobyl, the shorter version. You know that there's an HBO docu-series that goes through the whole Chernobyl situation. There's 5 parts to that. It's actually very good, very thorough as well. And now you're going to do a lab on fission and the power of uranium. So it covers nuclear reactors and essentially how nuclear reactors do melt down, how that could potentially happen. And then it goes into a little review of the nuclear equations that we were working on before. So let me share my screen here. So on page 166 in the blue book, you are going to go ahead and start there. And need to move this. So you need to go to the PhET simulation. So the PhET simulation, there's a couple different ways that you could go about doing this. This link, the link to the actual simulation that you want is available and is in its learning, okay? It says PhET nuclear fission. If you go to Google and you type in PhET, you will come up with all these simulations. The key is that when you look on the left, of course you want chemistry. You want to check both general chemistry and quantum chemistry, because now we're looking at subatomic stuff. And you want to make sure you check HTML5 as well as this Java via chirp. So this is how they're accommodating the fact that Flash no longer works. They have this as kind of an adapter to work on your computer. And using this adapter is how we're going to use the nuclear fission one. So down here, as I scroll, goes in order, alphabetical order. Here's nuclear fission. I'm going to launch it. And you're going to, again, follow the directions as they are written on page 166. Takes a little while to get this uploaded, as you can see. Patience, it's a virtue. There we go. So on the top, sorry, this keeps getting in the way. Just like the directions state, you're going to make sure that this tab is the one that you're using. Down here, you can see a energy diagram. So this is, we're looking at uranium-235, and this is the energy of one nucleus. So this is your y-axis. On your x-axis, you have the distance between daughter nuclei. So once uranium starts to, well, when we call it fizz, it's actually splitting. You'll be able to see the distance between the daughter nuclei. And it's just kind of a cool simulation. So the first question is, what happens when you hit it with a neutron? So this is my neutron gun. It's uranium-235. So let's go ahead and hit it, see what happens. So my parent starts shaking up a bit, and then it splits. And then the distance gets bigger between those two nuclei. You can go ahead and reset it. There we go. Oh, sorry, I'm looking, oh, here it is, reset, right there. So let's try it again. So we get the shaking, becomes uranium-236, right? So there's that transmutation from 235 to 236. So we have 3 of the 4 things. And now you can kind of look at the potential energy. So this is the energy that could be out there versus your total energy. And you should also notice that 3 neutrons are also here. Let's do that one more time, and I will pause it. So you got your 236, bam. So here's a daughter, here's a daughter. We get 2 daughter nuclei, but we also get 3 neutrons. So here's my legend. So 3 neutrons are also produced. So those are 4 things. So number 3, done. So now you're going to go ahead and, again, do what it says, look at chain reaction, and you're going to follow those directions. And then you're going to, on page 167, it goes to nuclear reactor. So this is where it relates to Chernobyl. So you can go ahead and play with this. And these are your control rods, and you can go up and down here. So this goes up and down. My control rods, if they're all the way out, I'm not controlling anything. This, if I fire my neutrons, they go ballistic. It gets crazy. And it, my temperature goes up, and you can see that there's tons of energy over here, and it's getting wild. And as soon as I am able to, eventually my temperature is going to be sky high, and now I can go ahead and put them back in, and it comes down. So one of the things that happened in Chernobyl was that temperature that was really high, that caused these cylinders that the control rods are in, so these little slots right here, to warp, right? They're made out of metal. They got really hot. What do metals do? Well, they thermally expand, they warp, they change their shape. And because of that, then when they tried to stop the reaction and put the control rods back in, they couldn't, they didn't fit. So that was one of the reasons why the meltdown happened, because they couldn't put the control rods back in. So the control rods are made of boron, and boron can accept the neutrons. So the boron, the control rods actually limit the number of neutrons that are being available to hit the next nuclei, uranium-235 nuclei. So you're gonna go ahead and do page 167, and then you're all done with the simulation. And you can go ahead and look at part 3. Hang on a second. I want to make sure that I'm sharing. So we did part 2. I introduced you to that. Part 3, what you're doing here is you're looking at how uranium-235 decays. This is called a decay series because it doesn't just automatically become stable. So when uranium-235 starts out, it goes through a decay process, a series of steps until it finally ends up becoming stable at lead-207. So you're going to go ahead and fill this out. So you start with uranium-235, you know its atomic number, you know its mass number. It tells you right here that it goes through alpha decay. When it ends, you end up with thorium-231, and that's right here. Okay, so you're going to start with thorium-231 there. So I can put in my symbol. My atomic number is 90, mass number is 231. And it's nice to have these columns with the atomic number and mass number because in the next page, you're going to end up graphing it. So it just kind of keeps it a little tidier here so it's easier to graph. So I'm going to start with now thorium. And it's going to go through, just like it says right here, beta decay. So it's going to throw out a beta particle. There's my beta symbol. You can find that on table O. And it's going to become protactinium. So I've got to make this 91. And 231. So now this is what will be put right here. Okay, so you'll keep going down and you should end, if you're doing your math properly, you will end with lead-207. So your atomic number will be 82 and your mass number will be 207. Then what you're going to do is come over here and actually graph it. And you can see I've already graphed the first 3 based on the chart that I just was helping you complete. So this is my atomic number on the x-axis, mass number on the y-axis. So 235 is where I started at 92. And then I used an arrow here, which is nice just so you can follow where you go next. Then I've got 231, thorium at atomic number 90. I go this way. So this is going to zigzag. Don't let it freak you out. And I hit 91 here with protactinium, and my mass number stayed the same. So you will see this decay series graphically, which is really nice. Don't forget to do this. This is just labeling what the elements are, right, based on their atomic number. So you can kind of see how it works out. How many times you end up having uranium versus thorium versus radon. And that's it. So let me know, email me if you have any questions.